Ben trovati a tutti a questa edizione del Prisma e oggi è un piacere avere con noi Giorgio Cipolloni e Luca Benigni. La prima parte di questo seminario sarà da parte di Giorgio e fatemi dire due parole su di lui. Dunque, Giorgio Cipolloni ha una lunga storia, comincia gli studi di matematica a Tor Vergata, sarà un bel cerchio, e dopo essersi laureato a Roma Tor Vergata si sposta in Austria, dove completa il dottorato con Laszlo Erdos all'Institute of Science and Technology austriaco di Vienna nel 2021 su argomenti quali le matrici aleatorie, di cui ci parlerà anche oggi, e si sposta poi negli Stati Uniti dove ha una fellowship, un research fellowship a Princeton e dopo un piccolo momento all'Università di Arizona come assistant professor è finalmente tornato in Italia, a Tor Vergata, proprio dove aveva cominciato, e adesso sta facendo un RTT, sta cominciando un RTT. Siamo molto contenti di aver Giorgio, che è una persona di altissimo profilo, con più di 40 articoli pubblicati, molti in giornali top. Ehm, Giorgio si occupa di matrici aleatorie, quindi eigenvalues, eigenvector statistics, fluctuation e questo genere di cose. Prego, Giorgio, ti lascio a te.
Grazie mille per troppo introduzione, eccetera. Grazie. È un piacere, diciamo, avere la possibilità di presentare un po' della mia ricerca. Adesso switch in English. Uh, okay, so yeah, the talk will be in English, and so yeah, like today, the goal is to present a bit of this field of random access. I mean, I will only be able to, me and Lucas, like just one part of this like very rich field, and the main message, as the title suggests, is like the ubiquity of these random metric statistics and that appear okay in random matrices, but also in many other at first are related problems, and like we both hope like to convey this message throughout the talk. I mean, if you have any questions, just please interrupt me. So. I put this link down here where like some of the slides are inspired to. It's a very nice introductory talk for, I guess, undergrads from Lucas, University of Montreal, which is in French, but like if you're interested, well, that's the link. Okay, let's start. So for the questions I will discuss today, this story goes back a while in the 50s by Wigner. So this is not the first time random matrices were introduced, even before, like in, for example, by Wishart, 28 looked at random matrices, but like these kind of questions, which I will discuss today, mostly motivated by this fundamental question that Wigner asked, which was like, what can we say about some statistical properties of eigenvalues or eigenvectors of large random matrices? In particular, the main question that he was interested in is about if one can see the emergence of certain universal patterns. And I will comment in a minute why he was interested in that in the first place. But if you think, I mean, this is quite a common theme in probability, like you see, for instance, like the CLT, it emerges from Gaussian random variable, and then it's natural to ask, uh, if we replace the Gaussian with another random variable, do we have a similar universal limit? So this is kind of the philosophy. So here we look at the Hermitian matrices n by n. So n here you should think this capital N to be a very large number. It's fixed but large. And Hn is Hermitian. So I will define it more formally in a second. But so the idea is that we have a large random matrix, Hermitian, and then we have its eigenvalues and eigenvectors. So what can we say about this statistic, these spectral statistics? So why, like Wigner looked at these Hermitian matrices? Well, he conjectured that these Hermitian matrices can be a toy model for the Miltonian Hamilton operators of chaotic quantum systems. In particular, his like fundamental revolutionary observation vision in the 50s was that, well, first of all, the energy levels of large quantum systems exhibit a universal behavior so that the microscopic physical details are not relevant, but the behavior is only determined by the basic physical symmetries. And the second step was that, okay, say, studying this object on a like physical quantum system may be extremely hard. Instead, he suggested randomness as a well toy model, but well, eventually it turned out to be not so toy, but like still can describe uh, this universal behavior of quantum system. So the main point of Wigner vision was that random mercies can be a toy model to describe the behavior, the much more difficult behavior of large quantum systems. And again, I mean, these kind of statements can be studied both
Sì, si è bloccato il video di Giorgio, adesso vediamo. E l'abbiamo perso completamente. Adesso-
Siamo senza speaker.
No, aspettiamo,
Adesso
confondiamo che non
lo
sappiamo.
recuperiamo.
Mi scrivo un messaggio veloce.
Yeah. I don't know what's the best. If you want, I can keep going every slides. I don't know if time is sensitive or not.
I would maybe wait 2 minutes
Yeah.
just to
Yeah, of
see,
course. Yeah.
and then
hear me now or
Ah, yeah.
è tornato.
sorry, yeah, like uh,
Maybe
unfortunately
forse
EduROM doesn't
Giorgio,
work.
suggerisco
Sì,
di spegnere il tuo video
ok, sì.
e anche gli altri, così magari avrai una connessione un po' più stabile.
Purtroppo EduROM ogni tanto fa un po' di scherzi.
Sì.
Vale.
Però se vuoi condividere comunque
Ok,
delle
non
slide,
so, sì, non so dove si era, cioè quando si è staccato.
un po'
Eh,
indietro, indietro, qua eravamo, quindi
ok,
poi
sì, ok, ok, riparto. Ok,
non
yeah,
proprio,
sorry
non
for
proprio
the minutes.
l'inizio, ma più o meno,
Ok.
certo,
Um,
prego.
yeah, so sorry. I mean, like, hopefully the ROM will not disconnect anymore. Well, we'll see. So, so maybe yeah, okay. To summarize, not to. But first, like, so to summarize this slide, so the idea is that the Wigner vision was that the behavior of these large quantum systems should be universal in the sense that the details, the microscopic details of the system are irrelevant, but only the main physical symmetries matter. And the main observation was that random matrices are a toy model like to observe this phenomenon. I mean, eventually that turned out to be not so toy. I mean, since we see that took quite many years to prove these statements, but like, so even though at first they seem related to the quantum system, we see that there are many things in common. And what I mentioned here is that here we look at large matrices, n by n, and two natural objects to look at are the behavior of eigenvalues vectors, universality, and so we'll focus on eigenvectors more in detail. By the way, please let me know if at some point something's not clear, like with the connection again, because I don't know what to do. But so yeah, there would be n by n Hermitian matrices, so the entries are independent, identically distributed, and with this normalization, so they are centered, they have variance 1 over m. So why this variance, why this scaling, this become clear in a second. So here in this histogram, this blue histogram, plotted the eigenvalues of our random matrix Hn. And you see that, well, it fits pretty well with this red curve, which is known as the Wigner semicircular law. So it's this curve I wrote down here. It's nothing else than alpha circle. And you see that there is a pretty good match. And just to state more formally, so this fact was found out by Wigner, 55, that's why it's known as the Wigner semicircular law, and say that for this class of matrices, so these Wigner matrices which I defined here, the distribution of the eigenvalue is universal and is given by the semicircular law. In fact, if we look, if lambda are the eigenvalues of our Wigner matrix Hn, if we look at how many eigenvalues are in a certain interval, then this converges to what you would expect. So it converges to the integral of the density over the interval AB. Once we rescale by 1 over the dimension. So you can think of this as a sort of law of large number type of result on a macroscopic scale, so that this convergence, I mean, is not sensitive to the singular eigenvalues, but it looks at the joint behavior of many eigenvalues. I will go back to this in a bit more details on like the different behavior on the eigenvalues on different scales. Okay, so now the question is that since now I related this semicircular law to the law of large number, like one can ask to what extent this semicircular law is really universal, like the law of large number converges to the expectation. So what happens if we change a little bit the metrics? Okay, so we will see in a second that indeed this is not so universal, because if we change, say, the variance of some of the entries a little bit, then we get something very different. Okay, so let's look at the Hn, which is divided into 4 blocks. So each block is n over 2 by n over 2. And let's look at the eigenvalue of this if we just change one of the blocks. So say we multiply the Hn1 by a factor of 4. So we just change the variance of one block, and we see that the answer we get, it's a complete difference. I mean, this new histogram has nothing to do with the semicircle. It's not just obtained by a simple rescaling or dilation of the previous graph, but it's just a complete different function, this limiting eigenvalue distribution. And in fact, so it's much less universal than the central limit theorem, because, for instance, in the CLT, if you rescale each one of the random variables, then you will just change like by a constant factor, just scale the limiting Gaussian. Instead here, the answer is completely unrelated to what we had before. Okay, so I started with this like claiming that Wigner envisioned some universality random matrix, and now I seem to say that, well, this is not universal. So what's going on? So maybe you're asking the wrong questions. Like, this is not looking at all the eigenvalues at the same time. It's not the right quantity to look at for universality. So let's see. Indeed, one can we have, okay, n eigenvalues where n is a large number, and then we can look with zoom in at the eigenvalues at three different scales. So what we have done so far is the macroscopic scale, so that we look at basically all the eigenvalues or order n eigenvalues. Say we look at n over 2 eigenvalues at the same time. So that's the macroscopic scale, which we have seen is not universal. Then there is the opposite scale, which is the microscopic, when we only look at finitely many eigenvalues. So order one of them. So here by order one, I mean independent of n. So say we look at the joint distribution of 5 eigenvalues. And then lastly, there is the mesoscopic scale, which is basically everything in between. If we look at n to the alpha eigenvalues, when alpha is strictly between 0 and 1. Okay, so now we saw that the macroscopic scale is not universal. So what can we say about these other two scales? So we can see that indeed, that's what we will see basically in the remaining part of the talk, is that this universality really emerged in the macroscopic scale. And there are several, but like the two main questions that I will discuss are what's the behavior of the largest eigenvalues, lambda n, say, if you order them in increasing order, and what's the distribution of the gaps of two nearby eigenvalues. Okay, so we will see that while at a macroscopic scale there is no universality, if we zoom in the microscopic scale, we do see the emergence of the universal behavior. I will not go into the mesoscopic scale, but I just want to mention that basically the closer you are to the macroscopic scale, so the less eigenvalue you look at, the more universal it is. So as you decrease the number of eigenvalue you look at, you will see the emergence of a more universal object going down to the macroscopic scale, where pretty much all the statistics that you can think of are indeed universal. Okay, so this is just a picture of how this looks like. So we look at drawn the semicircular law, so again a Wigner matrices. And then, as I mentioned in the previous slide, we can zoom in two different regimes. So if we zoom in on this side, here on the right side, so in this purple regime, we see the edge, and it's what is known as the Tracy-Widom distribution. I will comment on that in the next slides. And the eigenvalue here, since like the density decreases to 0, there is a different scaling. So this scales like n to the minus 2/3, like the distance between two nearby particles. So from the picture here on the right, you can see that the distance between the eigenvalues is actually quite larger than what we see in the picture on the left, the back of the spectrum. And the other question, this one what I mentioned about the gaps, is going to be instead in the back of the spectrum, so in this green regime, where we see what is known as the Wigner-Dyson meta-universality class, which emerged on a scale 1/n. So these are kind of the two scales which we look at. And maybe just to highlight one key difference is that if you look at the box statistics of the green regime, the density is basically flat. I mean, you can see this orange curve, which is the semicircular density. It looks like basically a flat line. Instead, like in the edge, on this right picture, there is this curvature effect, which causes these different statistics and different spacing. Okay, so these are kind of the questions, and now I will say something more about each of them. So before I go into that, is there any questions so far, or if I froze again, or? Okay, so if not, then I will move into each one of these questions. I will start with this purple region. Okay, so we look at the behavior of the largest eigenvalue. Okay, so the first question is to see, well, where this large eigenvalue converges to. So if you remember, like the histogram of the eigenvalues of this Hn are contained in the interval -2, 2. This is the support of the semicircle. And in the 80s, Fure, Eddy, and Komlos showed that indeed the largest eigenvalue doesn't go outside the interval, really converges to 2. Okay, so there are no outliers outside of this interval. However, these two, as I said, like comes from the same circular law, which we discussed before. It's not universal. And instead, like the universality really comes from the fluctuation around too. So the fluctuation around this deterministic limit. So this is what the surprising and striking observation like that Tracy and Widom found out in the 90s is that if you look at the large eigenvalue of this Wigner matrices, they looked at the case when the entries are Gaussian, where there are explicit formulas that one can use. Then we subtract the two, which is not universal, this expectation, and then if we rescale by the level spacing, then the distribution of this large eigenvalue, it's really universal, and is given by the Tracy-Widom law. This is what I denoted by TWS, which is a very complicated function. It's not explicit, but it appears in many unrelated problems. So now I discussed the emergence of this Tracy-Widom from random matrices, but we'll see. I will discuss also like many other, I will mention two other unrelated problems when this Tracy-Widom appears again. Okay, so going back to random matrices, like Tracy-Widom showed this remarkable fact, like for matrices with Gaussian entries. So like this is how this Tracy-Widom looks like. But then this was done for a specific metric, so R7 that is Gaussian. But then going back to Wigner vision, one can ask what happens if we change the distribution of the entries. If this is really universal, it should not depend on that, and that's indeed the case. I mean, that's what Soshnikov proved in '99, showed that if you look at these Wigner matrices, so the entries are independent but non-Gaussian, then the distribution of the large eigenvalue is universal and still given by this Tracy-Widom. And here I apologize, I mean, I mentioned just this work. I mean, after this, there have been really a plethora of works like trying to prove this kind of universality for more and more general models. But like I won't go into that and just stick throughout the talk to the Wigner case, to the simplest possible case, basically. Okay, and now, as I mentioned, I want to try to convince you that this Tracy-Widom law is really ubiquitous. So it appeared in this Gaussian matrices. Then by Soshnikov was proven that it appears like for a large class of random matrices. But interestingly and surprisingly, this appears also in many other unrelated problems. So I just mentioned two of them. The first one is the longest increasing subsequence. So we take a random permutation here between 7 numbers. And then we looked at the longest increasing subsequence, which in this case is this colored in orange, like 1, 5, 6, 7, for example. So then again, there will be a limit. So we take a long permutation in n numbers. So n is a large, sigma n is a random permutation. Then what Bike, Deift, and Johansson could prove is that if you look at the length of this longest increasing subsequence, a leading order is given by 2 square root of n. But then if we properly rescale, we see again this funny exponent 1/6, which is related to the 2/3 I showed you before. Then this also converges to the Tracy-Widom law. So the fluctuation of this length of this longest increasing subsequence, which is a completely different problem, also converges to Tracy-Widom. So the same distribution. And another interesting object that also where Tracy-Widom appear is the TASEP, which is the totally asymmetric simple exclusion process. So let me just briefly discuss what this process is. So we look at particles, say, sitting on the integers, and then at each step, one particle jumps to the left, if it can, and like, what does it mean if it can? So like, a particle can always jump unless there is another particle there. So if there is another particle to the left, the particle doesn't jump. And we repeat this process for n step. So then we look at the distance from 0 of the leftmost particle. And again, we see the emergence of this Tracy-Widom law. So basically under the same rescaling as above, so we center by 2 square root of n rescaled by n to the minus 1/6, we get in the larger limit. So if we look at many steps of this process, we see again the emergence of Tracy-Widom. So again, here you see that for yet another problem, you see the emergence of Tracy-Widom, even if the problem itself is not related to random matrices. Okay, so that's it for the edge. And now let's say something about the bulk, where again, well, we'll see that there is a new distribution emerging, but again, there is this ubiquity of this distribution among random matrices and more. I will be a bit more brief in this case, but like just want to flash some key names and facts about this. So let's look at the distance between two nearby eigenvalues, say in the middle of the spectrum. So we have this Gn is just the distance between the n over 2 eigenvalues and the n over 2 plus 1. Then we normalize by n so that this Gn is an order 1 quantity because the 1 over n was the typical scaling, the typical distance between nearby eigenvalues in the bulk of the spectrum. And for this object, Wigner conjectured that, well, the distribution of this Gn is universal and is given by this curve, which is known as the Wigner surmise. So it's this fairly simple curve, this wrote down here, which it seems to match pretty well this histogram. However, Wigner was wrong. So this is not the actual distribution. It seems it's close enough. I mean, you see that it fits pretty well the histogram, but it's not quite right. Indeed, Wigner derived this limiting distribution for 2 by 2 matrices. And then he said, okay, I mean, if it holds for 2 by 2, why not in the general case? And I mean, he was wrong, but not totally wrong, maybe. But the real answer, the limiting distribution of this n, was found only later in 61 by Godin, which shows that the distribution function of this Gn in the larger limit, again, for matrices with Gaussian entries converges to a new distribution, which again, it's very complicated, so very much like Tracy-Widom. So it's not an explicit function, but again, it's expected to be ubiquitous in mathematics and physics. Indeed, three physicists, Wigner, Dyson, and Mehta, that's where the name Wigner, Dyson, Mehta statistics comes from in the 60s, conjectured that the distribution of the gaps of this eigenvalue should not depend on the distribution of the entry of the matrix. So again, Godin computing the Gaussian case, and then they conjectured that if the entries are non-Gaussian, by some other distribution, under some assumption, it should still converge to now, I mean, this is not conjecture anymore, was proven about 15 years ago that for a large class of random matrices, this is indeed the case. So you see the emergence of this Godin function. It was proven by Erdős and Yao like in around 2010. So you see that has been open for about 50 years. So the edge was solved that maybe at first one also this
Aspettiamo un minuto che si riconnetta.
sorry.
Nessun problema. Ce l'abbiamo quasi fatta, no? Mancavano 2 slide.
Yeah, yes.
Carica.
So yeah, you can see that I just moved to Cerrai. I don't know clearly which are the connections that work. So yeah, but likely I'm basically done. So sorry. Let me try to push it until the end. So yeah, what I was saying is that so this um, random matrix statistics appear in many related problems like the Riemann zeta function and chaotic quantum systems. Like Lucas will talk more about the connection to chaotic system is even more clear, like for eigenvectors. So in this last slide, let me just summarize and give a brief outlook what that one can do. So that what we saw that the eigenvalue behavior of these large random matrices are really universal, and we see that so is the behavior of eigenvectors. However, I just discussed this in the simplest possible case of Wigner matrices, so when the entries are IID and there is no structure. But this vision is now proven also for some more general models. One important one is the random band matrices. There are these 2 important papers by Yao Yin and Erdős above and this year. However, we are still extremely far from original Wigner vision to show the emergence of these random matrix statistics for even deterministic chaotic models. So if you take the quantization of, say, the ergodic billiard, you should see the Laplacian on this billiard, you should see the emergence of the statistics, but this is completely far from being proved. And I should say that, so I focus on the typical fluctuation of the eigenvalues. However, there have been recent interest in fluctuation of extreme statistics of the maximal fluctuations of these eigenvalues. And 2 of the recent work, like part of there is this work by Borgad, Lopat, and Zeitouni, and then I had a work with Ben London about this fluctuation of extrema for specific non-Hermitian matrices. And then in this talk, I just focus on over-Hermitian matrices, but in the last years, there have been large interest also in the study of universal statistics for non-Hermitian matrices, when there are some similar conjecture in the 80s, where they conjecture again that the local statistics of this non-Hermitian matrix is also universal. And this has now been proven both close to the edge of the spectrum, which is in this case is on the complex plane, so it's a unit disk, at the edge, which I proved with Erdős and Schroeder. And then again, this happened before the bulk, because also in this non-Hermitian case, the bulk is up there. And quite recently, 2 years ago, in a breakthrough, Maltsev and Osman could prove the universality of these statistics in the bulk of the spectrums as well. But our understanding of non-Hermitian matrices is still much scarcer than the Hermitian case, so there are still many more questions that need to be answered in this non-Hermitian setting, so there is still lots of work to do. Last 5, 6 years have been really working in this direction. And with this, I want to thank you all for the attention and also the patience of this continuous disconnecting, and really sorry for that.
Grazie Giorgio per il tuo seminario. È stato molto interessante, a parte insomma i due momenti di disconnessione. Ci sono domande?
But
So I have just a curiosity, if possible, concerning the role of the constant 4 in page 5.
yes, so yeah, there is no role. I mean, of 4, it's just something different than 1. I mean, there should be something significantly. I mean, not 1.001. Otherwise, you see like small deviation from that. But like if you take 2, 3, like you start to see significant difference.
Okay, thank you.
Thanks.
Ci sono altre domande? I have a small curiosity. So, in the non-Hermitian case, you said that the behavior of the eigenvalues is universal. It's proven in the bulk. which kind of statistics are considered to show this universality?
So usually what one look at is the joint correlation function of, say, 10 eigenvalues. So like you choose a point well inside the disk, and then you zoom in on the fluctuation scale of eigenvalues, which in this case it's 1/√n, and then you look at the joint distribution of finitely many eigenvalues there. And in the Gaussian case, again, you can compute this explicitly, and then the goal is to show that if it's non-Gaussian, it behaves likewise.
Oh, cool. Thank you. Okay, if there are no other questions, I think we can take a small break of 5 minutes, and then we resume at 45 with Luca. And thank you. And let's thank Giorgio again for the nice talk, of course. So if you want, Luca, to share your slides already.
Yeah, I'll do that.
Maybe you go full screen.
Yeah, trying to.
So it's a view normally, and then.
Yeah, I'm confused now. The chromatin. Go.
Yeah, there it is. Cool.
Which it should see. You see my mouse also, right? Just
Yeah. All good. So we have 5 minutes of break, and I will take a break as well. For 2 minutes, I will be here in a second. Okay, welcome back to the second part of this seminar. Now it's the turn of Luca Benigni. He is not Italian, as you might have thought. So he's French. And Luca did his studies in Paris at the École Normale Supérieure Cachan and the Paris Sud d'Orsay. And then he did a PhD in Paris Diderot under the supervision of Paul Brugard. In 2019, he obtained his PhD. He had a small visit, a small stop in terms of length at the MSRI in Berkeley, and then I was at the University of Chicago for some time. And finally, from 2022, he's in Canada at the University of Montreal. As well as Giorgio, Luca's interests lie in random matrix theory and topics around that. So it's a pleasure to have you here and to continue this seminar about, I guess, eigenvectors at this point. Thank you, Luca, and please, the floor is yours.
Okay, well, thank you very much for the introduction and the invitation. So yeah, I'm going to keep going with what Giorgio talked about and focusing mostly on eigenvectors and going into a bit more detail, maybe into what Wigner's vision-wise on mathematical physics. And also at the end, I will try to give a sketch, a cartoon of proof on how to prove this universal result, right? Like these eigenvalues and eigenvectors, because the global cartoon is the same. Of course, the details are very different, but I'll try to explain the main ideas. So, as Giorgio said, this universal kind of random matrix theory comes from the study of quantum systems and even more disordered quantum systems. And here I do one slide, which is just the simple thing what you would need to do about quantum system. I'm not an expert of that, but what you start with the configuration space we call sigma. And even if you study, let's say, an electron in a vacuum, it would be in R3, or on the lattice in the metal would be Z3, for instance. And the idea of random matrix theory is to do the simplest model possible. So instead of something continuous or discrete but infinite size, we can do a one-dimensional box, let's say 1 to n, right? That's kind of the idea of this setting. And then if you look at the state space of wave function, it's just a vector, in this case, in R2 of sigma, so in Rn. Of course, if it's R3, it would be a more complicated function. But in our case, it's just a vector on the sphere, right? So a particle is described fully by just a vector on the sphere of dimension n. And so you have this Born rule, which I kind of put in a box, because I think it's important to keep in mind to understand some words, especially. I'm going to talk about localization, delocalization, or things like this. And the idea is to see an entry of this vector squared as a probability to find the particle somewhere, right? So of course, if the probability is high, then maybe it's localized in these entries. If it's low, then it will be delocalized kind of everywhere. That's kind of the idea of this thing. And then if you look at, let's say, dynamics or other the system, you look at Hamiltonian, which is the self-adjoint operator, and in our case of Rn to Rn, so just a matrix, right? So just a Hermitian matrix would give you the toy model for a quantum system. And disordered quantum system, the disorder can come from, let's say, impurities in your medium, or maybe an external field or something like this. It would just mean that you take a random Hamiltonian in some way. And of course, you have to decide how to put this randomness, and this is many different models. But that's how the study of random matrix kind of come from. It's like, if you take a Hamiltonian and we disorder quantum system in this toy model of 1 to n, this is just an n by n random Hermitian matrix, right? And so the entries of the Hamiltonian would be kind of transition rate, if you want, from a configuration to another. And then here to set up the same notation as Giorgio, lambda 1, lambda n are the eigenvalues, and they're also called energy levels in this setting. And then the eigenbasis, U1, UN, or normalized, which would be very important for different scaling, are what's called stationary states, because, you know, if you start in this state and you do dynamics with the Hamiltonian, you will stay on the dynamics in this state. Right? So that's just the eigenvalue eigenvector equation here. So what I call here the ground universality conjecture, which is maybe more of a belief than a conjecture in physics, because it's far from being proved and also far from being true. You can always find counterexample of this belief, but is the idea that disordered quantum system has mostly two behaviors. And I'm describing them here. The first one is called insulating phase or localized phase. It's just that eigenvectors are localized. And here I define what I mean by localization. It's just that you have a subset of entries, right, which is very small, and where almost all of the probability mass is. Right? So if you remember to think of an entry of an eigenvector as a probability to find a particle somewhere, this would just mean that with very high probability, the particle is in this subset of entries, which is very small. Right? So it would be localized on this set of entries. And if you look at eigenvalues, well, they kind of behave independently. So it is very different from what Giorgio talked just before. We have this go-down distribution, this kind of weird gap distribution, which is not at all the same as a Poisson point process. But if you're in this phase, basically eigenvalues are independent. And if you want a very easy example, which is the simplest model of random matrix theory you can take, you take a diagonal matrix with IID random variable. Well, of course, the eigenvalues are independent, and the eigenvectors, well, it's just one entry is 1 and the rest is 0. So the particle would be exactly localized at all times on one entry, right? So it's fully localized. And that's the simplest model you can take. It's actually hard to take a non-trivial other localized regime, right? Because even if you can add some off diagonal, you can start to be delocalized. In this case of Laplacian, for instance, it's just tridiagonal with just upper and lower diagonal, and the eigenvectors are kind of plane wave, are free to localize. So it's not always easy to construct more complicated one. I'll go to it at the end of the talk. And the other phase, the complementary phase, is a conducting phase. And now eigenvectors are delocalized, and I'm not defining it, because for now, the definition will be to be not localized. Okay, so you don't have this subset of entries that most of the mass is, but I'll give precise estimate later on. And your eigenvalues are strongly dependent, and more than that, it's always the same local statistics. It's vigorous on meta that Giorgio talked about, but this good distribution of gap or local statistics in general. And this belief is that, you know, for way more complicated disordered quantum system than random matrices, they will still be true. And you only have these two regimes. And that's this kind of belief. And as an example, I'm going to, with also Wigner matrices that Giorgio talked about, I'm going to consider a simpler example, which is a Gaussian Wigner matrix of Gaussian orthogonal ensembles. Right? And so an eigenvector can look like this. You see that, if you remember, right, this is a probability. And basically, well, the eigenvector can be anywhere with the same probability, right? Pretty much. There are some extremes, of course, but except that it's pretty flat everywhere. Okay. Okay, so what is this Gaussian orthogonal ensemble? So it's a very simple matrix. It's a symmetric matrix. I'm considering the symmetric instead of Hermitian, just for notation. And the entries are Gaussian. and they're independent, of course, up to the symmetry, right? Cannot be fully independent, otherwise it wouldn't be symmetric. And so if you think of this transition rate, it's just a complete graph, right? You can go from any state to any other, and with the same rate, well, not same exactly, but in distribution, the same rate, right? It's Gaussian distribution. Okay, and the 1 over n is the same scaling that Giorgio talked about, so that the eigenvalues are between -2 and 2 or the 1. Okay. So why is it called orthogonal ensemble? It's not an orthogonal matrix, but it's invariant to orthogonal conjugation. Right? This is a property of Gaussian vectors in general. Right? Like, so if you take this matrix, conjugate on the left, on the right by an orthogonal and its transpose, then in distribution it's the same. Okay, so it's a striking result. It's true for finite n, and of course it's only true for this ensemble. Right? If you want to be independent random variable, actually this is the only one to have both independence and orthogonal conjugation independence. And now, if you consider eigenvectors, well, they're a bit trivial, right? Because what this means in this box, it means that if I have an eigenvector and I rotate it however I want deterministically, then it's the same distribution. So the only thing possible really is that the vector is uniform on the sphere, right? Because I can rotate it as much as I want, I get the same distribution. So the only possible thing is that. And that is true, right? It's true for finite n. This is an n equals 3 kind of plot on the sphere. And the eigenvectors are truly uniform. And if you look at the whole eigenbasis, it's uniformly or hard distributed on your orthogonal group. Okay, so it's really, really uniform in this sense. And a very striking result, which again is only true for this model, is that the eigenvectors are independent of the eigenvalues. Okay, so it's very, very striking. Even though, of course, you have the eigenvector-eigenvalue equation, the properties of this model makes you independent from one to the other. So, as I said here, eigenvectors are trivial for this model, and this is only true for this model. Okay, so what does that mean? Right? If I change, of course, the orthogonal conjugation is wrong. So what do I do? Well, the idea is a bit different, is to take this as a reference. And what we can do is say, okay, we have the exact distribution in this case, so we can get some quantitative estimate, we can compute things because we have distribution, and then we can hope that asymptotically for other models, we can also prove this quantitative estimate. Okay, of course, even though the eigenvectors will not be uniform on the sphere, this is wrong for other models, well, maybe some distributional sense of entries, of maximum or others are the same, and we can maybe get that as universal result. Okay, and so let's see some of these properties that we can study. So the first one I put here was called a Porter-Thomas law in physics, but it's just asymptotic Gaussianity. It was studied in physics by Porter and Thomas, but even before that, actually, by work of Borel or Lévy, to just study an entry of a vector uniform on the sphere converged to a Gaussian. Right? That's kind of the idea. And so here, I put it in this sense. So if you take a finite amount of eigenvectors and finite amount of entries, then converge to IID, Gaussian random variable. Right? I put the absolute value because eigenvectors are defined up to a phase, of course. Right? So you need to choose this phase. I just choose it by taking the absolute value. Okay, so I don't need to have this choice. And that's an example of an histogram of an entry of an eigenvector. And then Diaconis-Friedman and Jiang actually pushed it to even grow I and j with n. Okay, so you can actually grow almost optimally, not fully. You can take the whole thing because, of course, you start to see correlation on the fact that they're on the sphere. But if you take little O of n of them, for instance, you still get this convergence. So one is what's called eigenvector delocalization or infinite norm delocalization. And in this setting, it says the following is that if you take, for instance, the maximal entry of an eigenvector, then its size is about square root 2 log n over n. Actually, this is more than just an inequality. You have also the lower bound. And so I try to think of this scaling. Right? It's kind of 3 scale. This is the square root n and the square root 2 log n. Remember that the eigenvectors are L2 normalized, right? So if they were deterministically kind of delocalized, right, every entry would be equal to plus or minus 1 over square root n. Right? This is as most kind of exactly delocalized it could be. And what this states is that it is not far from this. Right? The maximal is almost 1 over square root n, but you have some kind of small fluctuation, okay, which is square root 2 log n. And this square root 2 log n is not surprising if you look at this Porter-Thomas law, because it's the same as if you take an IID Gaussian vector, you would get this square root 2 log n over n. So it means that even at the level of getting the maximal entry, you still see that the vector is basically an IID Gaussian vector in some sense. Of course, it's some correlation, but they're very weak. Right, so that's an example of that. You see that the maximum is pretty close to 2 log n over n. In the symmetric case, you have some log n correction, so that's why it's not perfect. But you have this. And of course, you see that if you again think of this Born rule, whatever probability of a particle being somewhere, if this describes a particle, well, the particle can be anywhere, right? Like with basically almost the same probability to some small fluctuation. Okay, so that's a two example. So let's see another one, which is more complicated. How it looks, but if you think about it, this is also quite natural. It states, okay, well, I want to study a particle being somewhere. If I say this as some kind of density of probability, or not density, but as probability law, then I can ask how uniform it is, right? How close to uniform distribution it is. And the idea is to say, okay, I can take a subset of entries, and I can sum the probability mass and compare it to the uniform distribution. Okay, so it tells you how close to uniform it is on any subset of entries. That's kind of the idea. You can also look at how orthogonal two eigenvectors are. Of course, it's 0 if you sum over all the entries, but here is basically stating that they're orthogonal not because some are plus and some are minus, but really everywhere they're almost orthogonal. You can project onto any subset and close to orthogonality. Sometimes it's called quantum weak mixing in this setting. And you have an explicit rate of going to 0. And this is the idea. So this quantum unique periodicity, this name actually comes from another field, which is quantum chaos theory. This is a big conjecture by Rudnick and Sarnak that basically state that the Laplacian, the eigenvalues and the eigenfunction of the Laplacian, on some negative curved Riemannian manifold, but you can also think of stadium. This is also true for some negatively curved stadium, like this one. Actually, if you look at the probability mass of an eigenfunction over size A, well, it converges to the uniform measure, or the volume measure, along A, but the limit is a bit different. Here we go, the dimension to infinity, but here, of course, we're already in it's an operator, it's already infinite dimension of infinite eigenvalues, but it has this, the energy goes to infinity, so you get the higher and higher eigenvalues. It's a bit of different in this setting, but it's still a comparison of the probability mass of an eigenfunction to the uniform case. Okay, so it's an example of relatively high energy eigenfunction, and see it starts to be more and more uniform if you go further. So this is a big conjecture. It's proved only for very specific surfaces in this kind of great line of work. And there's more work if you don't do the whole sequence, but like through subsequences, for instance, so averaging over K, especially in the 80s by Schillmann, Zeldich, and Anatol and Masson for more recently for the irregular graph. But it's still, to my knowledge, quite open to have this exact limit in this setting. So this is kind of a link between quantum chaos theory for eigenfunction and eigenvectors or random matrices. There's also a conjecture for eigenvalues, the Bohigas-Giannini-Schmidt conjecture, which states that also, if you look at the eigenvalue statistic, they behave like random matrix theory also. But this is also wildly open for this set. So we can do another thing for eigenvectors, and we can generalize in a way this quantum unique periodicity by looking at what's called the eigenstate thermalization hypothesis. So it was done by in physics by Deutsch and Cerrai in the 90s. And the idea is the following: is that if you take any deterministic observable out of, let's say, Barnett norm, then the eigenvector is going to diagonalize this matrix almost up to some error, right? So it's really, you take any observable deterministic, and the eigenvector will be an almost diagonalization basis for this observable. That's what like thermalization would mean in a sense. There's an example here. Here I did all the spectrum. So each point is for eigenvector of one eigenvalue. So this is -2 and 2, if you remember the semicircle. And I look at every eigenvalue and I compute this thing for some A I've chosen. And you see that it's very close to the black line, which is the trace normalized, and up to some fluctuation, which has this dashed line, which is basically this order. Okay, so you really, among the whole spectrum, this is true. And you have this. And this is also the true kind of bound, because you have a central limit theorem. So if you renormalize, this converges to a Gaussian. Right? You can see it, for example, here. Actually, I think this histogram is averaging all of them, but you can also do for each separately. And you still see this Gaussian distribution. Okay, so this is examples of things that one can prove: delocalization, Porter-Thomas law, ETH or QUE, or a natural question you can ask about eigenvectors. And so this is, of course, all true because you have the exact distribution of UK, which is uniform on the sphere, and so you can get all of that. But now, of course, you can ask, do these properties hold beyond Gaussian ensembles? That's the question that Giorgio asked at the start. And I'm going to stay in the same setting of Wigner matrices, which is kind of the easiest case you can do. So symmetric or Hermitian, independent centered, Burns 1 over n. I'm going to suppose that every moment is finite. For the results to be true, I'm going to state. But if you want to have one example in your mind, and I think that's the best example to take because it's kind of the hardest example you can take, is just to take a plus or minus one matrix, right? Like a Rademacher matrix. Why? Because this is very easy to see that it's not orthogonally invariant, right? If I rotate a plus or minus one vector, it's not going to be a plus or minus one vector. There's no reason. So of course, because of that, the orthogonal invariance is wrong. But if I give these two pictures, I couldn't tell you which one is Bernoulli and which one is GOE. Right? They look the same. And the goal would be to prove every quantitative estimate for GOE in this context of Bernoulli. Okay, that's kind of the idea, or even Wigner matrix in general. Of course, for finite n, this is wrong, that the eigenvectors will be uniform on the sphere. Right? This is not correct. But maybe asymptotically, we can hope for this quantitative estimate to be true. It's kind of the overall idea. And indeed, they are. So if you look at the infinity delocalization, this kind of 3 scale, which was kind of 3 barrier to reach, the first huge breakthrough was to get this square root n, because this really gives you the delocalization, and this is what truly gives it to you by Erdős, Stein, and Yao, starting in 2008 and 2010 gave you this kind of work. Then the square root log n was done in some cases by Van Wu and Ke Wang, and then myself and Lopato, we did for everywhere in the spectrum for pretty general Wigner matrices, and we get square root log n, and even we could get the optimal constant. Right? So actually the constant is also universal in this setting. You have the optimal bound of square root 2 for this, let's say, Bernoulli matrix, for instance. This is also true. For the Porter-Thomas law, also, there's been quite a lot of work on that to prove the joint asymptotic Gaussianity of entries. And it's been done in a series of work with different kind of observable and different set of INJ. And this is, okay, not maybe fully done in Marcinec-Yao. There's still technically not fully done joint fluctuation, but we're very close to it with this work. Okay. So for QUE, I'm just rewriting them, but basically this is also done, right, in a series of work. So for QUE, especially Bourgade and Bourgade in a very nice paper starting to look at this more closely, and we finish it with Patrick. And at the same time, Giorgio with Erdős, and Schroeder prove the ETH, which is more general than QUE, because if you take A to just be, let's say, a projection onto the subset of I, this would recover exactly the same bound, right? So this is just more general. Was also done in a series of work to get more and more general setting. And the fluctuation is also known. So actually, there's a paper, okay, here I said the one by myself and Giorgio together, where we look at the joint kind of convergence of different observable like this. So for different A's and for different K and L, you can look at how Gaussian and independent they are, and an explicit covariance structure that appear from that. Okay, so basically, all the estimates I told you for GOE now are known in a pretty strong way for Wigner matrices, and actually even more general case. Okay, so the idea now for the rest of the talk will be to give you an idea on how to prove this thing. Okay, so how to prove universality for eigenvalues and eigenvectors. The cartoon of the proof is the same, of course. As I said, some details are very different, but the whole picture is kind of the same. And there are many different proofs, right? So Giorgio talked about the Soshnikov proof of the edge, or although I'm going to talk about the kind of more recent, the Erdős-Yao kind of program of proving universality, okay, which is very, very powerful in this setting. So this box here is the box of Wigner matrices for me, okay? And my Bernoulli matrix is here, that's this dot, and I want to prove, let's say, eigenvector delocalization, I want to prove the Godin distribution for gaps or something like this to this matrix. And the question is, how can I do that? Okay. So the first step, which is a bit of a cryptic thing I'm saying, optical control on mesoscopic scale. Okay, I won't go into detail too much what I mean. In the next slide, I'll explain a little bit more. But it's just saying that, if you work hard, do some linear algebra, some probability on the matrix itself, you can go pretty far. You cannot get everything you want, but you can go pretty far. For instance, the 1 over square root n delocalization can be done like this. Okay, you just need to work quite hard on the matrix, and you can do that. But if you want, for instance, the asymptotic Gaussianity, the Porter-Thomas law, you cannot just get it from that. At least we don't know how. You need to introduce something else. And the idea is that, okay, what is the case where we can know everything? It's a Gaussian case, right? The GOE is great. We know everything. It's uniform in the sphere. It's great. And so the idea will be to introduce some Gaussianity in some way. So how do we do that? Is by saying, well, I can define a dynamics, will be some Gaussian process, some kind of what's called Dyson-Browne motion, that will introduce some Gaussianity and will help me, because of this Gaussian kind of computation I can do in some sense, get the result what I want after some time t. Okay, so I'll start with some Wigner matrix, and I'm going to do some dynamics, and then compute what I want after some time t. But what's very powerful is that t doesn't need to be big. It cannot be too small, cannot be below 1/n, but it can be less than 1. So you can have a pretty small Gaussian noise, and you're able to compute all the different statistics that we told you with Giorgio, right? The gaps, the local statistic, the edge, the eigenvectors, the distribution, the delocalization, everything. Will be able to get it through these dynamics by just doing some SDE method, PDE method, like this, the dynamical method. Okay, that's great. But I told you that HT, right, has some Gaussian component, right, a little one. Even though if it's little, it still has one. But of course, a plus or minus 1 matrix doesn't have any Gaussian component, right? It's really singular density. So I cannot get this result directly because W, it's not a HT, right? It's not a HT of some process. I cannot go back in time with the plus or minus 1 matrix. So what do I do? Well, I said that I can choose my initial condition so that after some time t, I land close to W. And I'll explain at the end what I mean by close. This is blue disk here, what it means. But it means that everything in this blue disk, I can transfer all the statistics I want. Okay, it'll be difficult or not, but let's say the gap, if it's true for HT, it'll also be true for W. The eigenvector distribution, if it's true for HT, it'll also be true for W. Okay, and so that's what's very strong is you have this thing of the Dyson-Browne motion, sometimes called the density of Dyson-Browne motion, which means that for any Wigner matrix, you can find one such that after some time t, you land close to it. Okay, so that's kind of the idea. So you have these 3 steps where first you do some pretty intense linear algebra probability to get as close as you want to optimality. Then you do these dynamics, which is more of an SDE, PDE method to study this kind of Ornstein-Lindbeck process. And then you do some more linear algebra, Lindenberg style exchange to go from HT to your matrix W that you want. Okay, so in the last couple of minutes, I'll explain very quickly every step, okay, what it means. Okay, so the first step, okay, of course, maybe I can take that. But if you believe in this blue disk where you can transfer estimates, well, if GOE is here, right, everything in this disk is also known, right, because I know everything for GOE. So everything around it I also know for it. Okay, and that was one of the proof by Tao and Wu of universality, which was stating that in this blue disk you get universality. Okay, and then Eliash and Yao, through more work and actually even like a common work with them, did all of Wigner matrices together by combining the 2 methods to prove that. Okay, so the first thing is this optimal kind of control on mesoscopic scale. So what does that mean? Well, you can consider the resolvent, right? W minus Z minus 1. Remember the W is symmetric, so you can use the spectral theorem to just write the resolvent like this, right? So you have UK star and lambda K minus Z. And now you want to have delocalization, so you want to bound an entry of an eigenvector. So that's what I want to bound. Well, what can I do? I can do something trivial, right? Lambda minus lambda is 0. Eta square over eta square is 1, so I just write it like this. Okay. But now this is a positive value, so I can just sum of them and have it bound. But now if you look at this, there's just the imaginary part of this. Okay, so I can bound an eigenvector entry by this eta, and then this resolvent apply to lambda L plus I eta. Okay, so the idea is how low can you take eta for this bound to have what you want? And if you look at the bulk in the middle of the spectrum, you can go all the way down to n minus 1 plus epsilon, and you can prove that the resolvent is bounded. And so you do get that this is bounded by n minus 1 plus epsilon. That's how you get the 1 over square root n. And at the edge, the scaling is a bit more complicated. It's what Giorgio told you about. So this 2/3, it also appears here. And you can go down to minus 2/3, but the resolvent is also small of square root n eta. So n 1/3, n minus 2/3, n minus 1/3 gives you n minus 1 again. Okay, that's how you can get this n minus 1 plus epsilon for eigenvalues, for eigenvectors. And this, you can do it kind of by hand in a way, or you don't need these dynamics or others to do that. If you want the optimal square root log n, this is harder, but you can still do it. You just need to go all the way to the optimal. Instead of n epsilon here, you have to do log n. But if you want the optimal constant, for instance, we don't know how to do this. And so we're going to use the dynamics to do that, to get really stronger kind of result on eigenvectors. Okay, so this can also be done for the ETH. This is just very similar, except instead of one resolvent, you need to understand multi-resolvent type of things. Okay, maybe one slide about the dynamics. This is the following. So this is called Dyson-Brand motion, or the Ornstein-Uhlenbeck version. So it's an SD on matrices here, and B is a symmetric matrix with independent Brand motion up to the symmetry, of course, and with an Ornstein-Uhlenbeck version. So this allows you to have GOE as a really invariant measure for it, right? Like if you start with GOE and you go through this flow, you will keep going being GOE, right? So you have an invariant measure which is GOE, and so you can expect convergence in some sense to GOE when time grows. But what's very powerful is that if you look at linear local and microscopic behavior, you go to equilibrium very, very fast. Okay, with T it can be small. It's kind of the idea. And what is nice about this kind of dynamics is that the eigenvalue and eigenvectors follow an explicit type of equation, an SDE. So they're pretty complicated. Particularly the UK, depends on the lambda k's also. So you need to understand both to understand eigenvectors. But it's explicit, so you can do some computations, some different methods, coupling argument or dynamical PDE method to study that. And so after some time t, which is less than 1, you can get everything, almost everything at least, for ht. Okay, so for these dynamics. Okay, that's kind of the idea. And so maybe to finish, how do you transfer one step to the other? Right now you have your result for ht, but you want to go back to your Bernoulli matrix. The idea is the following: is to say we can find an initial condition such that the low is close to W. And what I mean by close is that the first 4 moments are basically the same. So the first 3 are exactly the same. And the 4th is not exactly the same, but it's pretty small. Okay, so it goes to 0 with when n grows. That's the idea. Okay, well, that's great, but what do you do? Right? But the idea is that you think of the central limit theorem. Well, the central limit theorem tells you that if the expectation is the same and the variance is the same, right, then my sum of IID is the same as the sum of IID Gaussian. Right? And then I can just prove CLT this way. Well, it's a Lindenberg proof of the CLT. And the idea is to do the same, but we're going to take our matrix and one by one exchange the entry of our matrix. Right? So it's going to W and then switch 1 to W. Then the H, we switch W, and we do it n plus 1 over 2 times. And then we get to go from the matrix H to the matrix W. And now with some, Taylor decomposition, we need to understand how an eigenvalue or an eigenvector behave when you change one entry of your matrix. Okay, and of course you have these properties that the distribution are close, at least up to 4 moments, and hopefully it's enough, and it is enough. Maybe one thing to say about eigenvectors is that if you look at how an eigenvector entry behave with respect to change in the matrix entries, well, it's not great, although it's finite at least. But if, let's say, lambda k and lambda L are very close together, then it can be huge, this derivative, right? And so it would mean that it would change a lot. So for instance, you need to understand the eigenvalues very, very well to understand the eigenvectors, which is the opposite of GOE, where I told you that the eigenvalue and eigenvectors are independent completely. So when you don't have this orthogonal invariance, the eigenvalue negatives become dependent, of course, and you even see it in the analysis. So you need to understand the eigenvalues to understand the eigenvectors first. Okay, so it's kind of the 3 steps. And maybe in 1 minute, I have one last slide, which is about other models that Giorgio talked about, like band matrices, or here to another one, which is what physicists like to do, to not just study one model, which is delocalized or localized, but they like to have modeled the transition from one to the other, right? Transition from localization to delocalization, to model the Anderson transition, for instance, model, which is one of the big problems in mathematical physics, let's say, to prove. And I take 2, so one which is easier, which is this one's bipolar model, which is kind of the simplest model, which is non-orthogonal invariant, which is a diagonal matrix plus a GOE, let's say, or a Wigner, with some time t here, or parameter t. So if t is very small, then basically the diagonal only matters, and so eigenvectors are localized, and the eigenvalues are basically the same. If t is very big, is order 1, then the Wigner matrix matters, and eigenvectors are fully delocalized, and I can do a universal, that's what you have here. So you go from fully localized to delocalized. But then you have an intermediate regime, which is quite interesting, where the eigenvector is somewhat localized. Actually, physicists still call it delocalized, but it's a bit localized like this. And eigenvalues are still universal. And so it's kind of an interesting transition where there's one for eigenvalues and one for eigenvectors. So it's an example where this universality conjecture is a bit wrong, but it's a bit different, because you have a case where you have eigenvalues that are universal, but eigenvectors are not localized in some way. And yeah, a very important model, because it's also closer to the Anderson model in some sense, is band matrices. So it's just a matrix where you just put the randomness in the band here. So there's geometry in your matrix. Everything else is 0. And very, very recently, there's been quite a lot of work to prove a conjecture, which is that if W is less than square root n, the eigenvectors are localized and the eigenvalues are Poisson, so basically independent. And if W is bigger than square root n, the eigenvectors become delocalized and the eigenvalues are universal. Okay, so here I put only the last paper. It's quite a big program. There's been many, many papers for the past 5 to 8 years, actually, almost 10 years, actually, to prove this conjecture. But it's something which is now pretty well understood in this one-dimensional case of transition. So it's an example where physicists are kind of quite interested into this thing. Okay, so I think I'll stop here, and I'll thank you for your attention.
Thank you very much, Luca, for the nice talk. Are there any questions? So I have one question. So the controls at the mesoscopic scale, where do they enter finally in the program?
Sorry, I didn't hear the question. Where do they?
So you have the step 1 in this program was about getting some mesoscopic controls, optimal controls on the mesoscopic scales. And this, where do they enter in the following steps?
Yes, so basically, where they're important, it's here, right? So I told you the rich local equilibrium in short time t, right? I tell you this.
Yeah, right.
But of course, the t where you reach local equilibrium will depend on the control you have on your resolvent. Right? So let's say you have a control of down to n-1 plus epsilon, then you can take t, which has to be bigger than n-1 plus epsilon. But now,
So
if your control is worse, let's say you control for n-1/2 plus epsilon, which is worse, right? Then you have to take t, which is bigger than n-1/2 plus epsilon. So if you want how big your Gaussian component needs to be, will depend on how good your control is, like this. So if you want to really reach optimality, you need this optimal control first as an input for your dynamics. And that's kind of the idea. I didn't explain this point, but that's a good question.
Just curious.
Yeah, that's a good question. You need it for the dynamics kind of to work, right? If you don't have this control, the dynamics, you don't know what to do, basically. That's kind of the idea.
Thank you. Are there further questions?
Maybe I have a question, just a very general one addressed to both Lucas and Giorgio. You have described very nicely the results obtained of this topic in last 50 years. So it seems to be a well-studied topic. So what is at the present time the insight about Wigner's original vision, according to which symmetry properties are those who actually define the behavior of the system? So we have seen that these distributions, such as the Tracy-Widom, Godin, were derived for random matrices, but appear also in other very different models. Is there any insight why is that? Is just an accident? What is your vision?
I don't know if you want to go on, Giorgio.
I can start and like cannot.
Sure.
Well, I mean, a bit what Luca said is more of a general belief, like that these are the only two kind of things that appear. Then, like there are in physics huge amount of numerics, like that. For many much more physically relevant problem, like these are the two kind of statistics, like either you are delocalized with randometric statistics or like localized with Poisson. And so, yeah, even in basically just chaotic deterministic systems, that what appears like that. I mean, also what I mentioned, this connection with number theory, there is no, I think, fundamental reason why it should be like that, but it happens to be, I think. But yeah, Lucas, I mean, I guess if something.
Yeah, no, I think that's a great question, and I don't think we have a good answer. I think so.
Right,
with all this
right.
work of validation, yeah, I think we now have a good understanding on why there's universality at the scale of random matrices. So it's only on this type of
Right.
matrices. I think this is quite well understood now. Not perfectly, of course, but well. Now, I think there's a big mystery both in math and in physics, right? So I think physicists probably now is just an accepted thing for them, right? Like that things are universal, and because numerics and others is quite easy to see, and well, yeah, this is a vision for 50 years. But I think mathematically this is not understood at all. I think it's one of the problems, because seems to have a true link between chaos, repulsion, and random matrix theory in some way, right? Which is not completely clear, right? Like, and why is the zeta function chaotic? Also, is not clear.
Right.
Like, this is not a good question. It's a good question, but it's not. We don't have a good answer. But and I think this is one of the main things. That's why in the title we put mystery, right? Because I think it's truly it's still a mystery. When you can do computation and you can understand mathematically why, I don't know, the length of the increasing subsequence is given by Tracy Widom, but I don't know even if the main authors of this paper know like truly why is an heuristic and insight why this would be the case, right? Like
Right.
and this is true for example, that if you take the in quantum chaos theory, right? Like so you have this thing about eigenvectors, but eigenvalues also, you have a similar conjecture that there should be random matrix theory like by Politecnico and Schmidt. So the fact that they appear in deterministic sets, right? Like because even in physics, I think numerics are basically random. If you take such high dimension or disorder or stuff like this, you have some randomness appearing. So you can hope that random matrices are a good model. But they seem to even appear for deterministic things, right? Like let's say for chaotic stadiums or for the zeta function or things like this. And this is true mystery, I think, which is not understood at all, to what I think at least.
Right.
Thank you.
So I would suggest that we thank both speakers again for the nice contribution. Thank you very much.
Mm-hmm.
And so this is, we will resume with Prisma also in 1 month, and where we will have a contribution by Ilya Chevirev, that is now in Trieste at CISA, and Hao Shen, that will give his contribution as well.
Okay, well, thank you very much.
Yeah. Thank
you
Yeah.
very much, really. It was very nice, very nice.
Yeah. See you. Bye. And sorry for the internet.
It happens.